So with this one actually starts out a lot like a problem I talked about the other day where I said, like writing how many of each one there are, but it went ahead and gave that part to us. If I start this problem, I would start this by looking at these and seeing what's the same. And I'm going a little bit quicker. Usually I'll give you time to look at this. In all of these, the minimum dot is the same, the Q1 dot is the same, or Q1 line is the same, and this outlier dot is the same. So that can narrow things down to me really quick, where I'm looking at, I need to choose where this one is, and I might need to look at my Q3 and my median. It was determined that the largest observation, 93, is an outlier because of this. So they showed you the work to calculate to see if it is an outlier. So this bar right here, does it go to 87.125 because that's what I calculated? What does it go to? It goes to the highest number that is not that far. So 87.1 something would be like here. But I need to go to the last dot that actually is in the data set. I don't know what the number is, but it's somewhere between 60 and 70. So is this where my bar should end? No. Between 60 and 70, yes. Between 60 and 70, yes. Between 60 and 70, no. So just by looking at that, I've narrowed it down to C or D. I'm going to talk through, I could get the answer by just doing one more thing, but I still want to talk through all pieces of it. There are 27 numbers. It gives me, if I added all those up, I'd get 26. So when I'm doing median, how many are in each half? How many numbers are in each half when I split it? So between the 13th and 14th number would be my median. There's 6, there's 10, there's 16. So somewhere in this bar is my median. I could now go through all these. So I know that it's somewhere between 20 and 30. This one's between 20 and 30. This one's between 20 and 30. C is not. D is. E is not. So I know at this point that my answer is D. But I'm going to keep talking through it because not everybody would have started where I started. So to get my Q1, if there are 13 numbers here and I'm splitting it, my Q1 would be at the what number? What's my math thing that I can do to figure out where the median is? Like if I have 152 numbers, I can figure out where my median would be by using what? N plus 1 divided by 2. So that first half has 13 numbers. Well, 13 plus 1 is what? Divided by 2. So the 7th number is my Q1. Well, so it's not the first bar, which means it's going to be somewhere in this bar. And then I could go backwards, and this would end up being the 20th would be my Q3. Or I could count back 7. 1, 2, 3, 4, 5. It's going to be in here. And use those to line it up, I'm still going to end up with the same answer, which is D. So this is another good example of using the number in each bar to be able to find a little bit more detail, like I was talking about in one of those other problems yesterday or last week. All right, number 40. Maybe a little bit surprised that this was the 20th, this question. But it's not a perfect answer, but there's definitely a best answer. Where different estimators for a parameter are being evaluated, the true value of the parameter is 0. So we're going to be doing simulations, and we want to know which one is the best. Well, if the true value of the parameter is 0, then we want our distribution to do what in relation to 0? be centered around 0. So here, this center looks good. This center definitely looks good. Maybe not perfect, but good. This center is definitely not 0. This center, I wouldn't choose it as my best, but it's not as bad as that one. Here, same thing, my center is definitely not 0. So it's definitely not D and E. The other thing I'm looking at, if I want a good estimation of it or a good distribution of it, is so my center should be centered where it should be, and I also want a what? So I'm talking about center, what's the other thing I'm going to talk about? If I want a good estimation of the spread, and I want my spread to be what? Small. So here, my spread is too big. Here I have a small spread. This spread is too big compared to the other ones. This one I have a small spread. This one I have a small spread. So what's my best answer? It's not perfectly symmetrical around it, but of those, that is by far the best answer. Is it always going to be centered at 0? No, it's only centered at 0 because it says the true value of the parameter is 0. All right, 24. This problem is very important in the fact that a problem that was very similar to this could be wrong. There's one thing about this problem that it tells us that lets us do something. If I say I've got a distribution here of sophomores and a distribution here of seniors, and I've got box plots drawn, can I say that there are more seniors that are whatever up there than there are? It's like, let's pretend that this is seniors and sophomores. Can I say that there are more sophomores above 70 than there are seniors? Can I say that? No. This is my picky thing. I cannot say more if I don't give you more information. But I could say there is a what? A higher proportion or a higher percentage. I can't say more unless I know how many of each one there are. So this problem says, and if it didn't say that, we could not make most of the associations that this problem is asking us about. And I want you to understand that because it would not surprise me at all to see a problem like that on the AP exam. Now, interquartile ranges. Can I talk about the difference in the quartile ranges, interquartile ranges, if I don't know sample size? I can still talk about that because it doesn't tell me there's more here or more there. So interquartile ranges are the same, yes or no? No, I can look at that picture and very obviously tell that from here to here is not the same as from here to here. The range for one is bigger than the range for the other. Both of the ranges are from 0 to 90, or from 10 to 90, those are the same. So all of these say more, and none of these three we could have done if it didn't tell you they're from the equal sample size. All right, so sometimes I'm still going to write it not as more. I'm going to write it as percentage because I think it's easier to talk about that way. Greater than 70. Alright, what percent for species A is greater than 70? Because here's 25%, all I know is it's less than that. What about for species B? Well, is less than 25% more than greater than 25%? No. Because it says or greater, well, that one's not greater than that one. Oh wait, more, sorry. Greater than 40. What percent of species B are greater than 40? Sorry, a B. Sorry, I'm reading here. All I know is less than 50%. What about more with species B or species A? More than 50%. Is there more in this one than this one? And that says there are more petal lengths here than here. Well, less than 50 is not more than greater than 50. And then my last one, less than 30. So for species B, what percent is less than 30? More than 50, what percent, about what percent is less than that for species A? About 25%. Is that one more than that one? And that's one that you could, it's not a hard problem, but you can very easily lose yourself if you're not writing the little bit down that I did with the greater than 25, more than 25, that kind of thing. If you're trying to do that one in your head, you could get lost without meaning to. But I like to look at this as just comparing percentages and not total numbers because that applies to all of them. 39. This is a problem that I have seen often. I've probably seen this problem shown like 4 different places. Except this problem gives more information than any other problems that I've seen this problem with the exact same information, but this problem gives more than any of the other ones I've ever seen. So we've got 2 different things. We've got adult male gray whales. Says they're approximately normal with a mean of 18,000 and standard deviation of 4,000. And then we also talk about adult male humpback whales. Says again that they're approximately normal. It has a mean of 30,000 and a standard deviation of 6,000. A certain adult male gray whale, which means we're over here, weighs 25 or 24,000 kilograms. So I've got an X in this category. It's 24,000. I honestly think this problem gives you too much by saying, usually I would see this problem like the same percent that have less than 24,000 kilograms for a gray whale would have what weight as a humpback male. And you have to understand the fact that you have to go through z-scores to get there. I think it gives you too much to tell you, hey, use a z-score to get there. So I can now switch all of this to a z-score. What's my general equation for z-score?
X minus mu over.
Over what? Standard deviation. So my x is 24,000. My mu is 18,000. Divided by 4,000. Well, that gives me 6,000. 6 divided by 4 gives me 1.5. So now it's just saying a z of 1.5 would give you a value of what, if we were talking about the humpback males. So now I'm just going and saying, I know my Z is 1.5. Now what is my X? And 1.5 times 6 gives me 9, and we end up getting 39,000. Just a quick side note here. This problem said randomly or normally distributed. Can I directly compare two things with a z-score if they are not normally distributed? Kind of. Go back to, if I said these are your test scores for stat and these are the test scores for bio, you can figure out if you did better relative to the other people in one class or the other. That's using a z-score. But the step that you cannot do is take the next step with a z-score. So what would we typically do with a z-score? Get a percentile. I could not find a percentile if I didn't know that they were normal. I can make them z-scores and compare them. I just can't go on to percentile. So z-scores can be compared if it's not normal, but we can't go past that. Number 6. And get out your orange sheets. I'm going to talk about a couple things on the orange sheet really quick. I want you to find something that looks the most like this problem on your orange sheet. What is that the equation for? Should I actually tell you? Binomial. That is binomial probability. That's like pretty much the only thing on that entire sheet that said this goes with this. The one thing that is helpful that I want you to make the association with, immediately under that, it has an equation for what? Just in general. What kind of are you mean? And what's right under that? Standard deviation. What do you think that is? If we have binomial probability here and then directly under it a mean and a standard deviation, what do you think those are the equations for? Mean and standard deviation of a what? Binomial distribution. They do group things together, they just don't label them. So that's your one thing to help you is your equation for binomial probability immediately underneath is your binomial mean, your binomial standard deviation. Okay, so let's look at this problem with the equation that you have in front of you. A fair coin is to be flipped 5 times. Well, that's our what? The first 4 flips land heads up. What is probability of heads on the next, the 5th flip? So in this one, this is saying that this is our n. What is the 1 as far as our equation? The equation sheet calls it k. I usually call it what letter instead? Just the obvious one, x. It doesn't really matter. But what does x mean in binomial? So if we were following the equation the same way it is, this is not what the problem would give us. It would have these two switched with the way your equation sheet gives it to you. Does that really matter here? No. So if I were writing what this problem is talking about, I would, giving some association here, I would say this is a binomial equation where you select 5 and you have exactly 1 success. We'll call it either heads or tails, which is not exactly what the problem is talking about. What do you think that is the equation for? It's been a while. What kind of probability is this? What kind of probability do you think this is? Alright, so I'm giving context now. That doesn't mean this is exactly what it was, but I'm giving context so we can kind of associate. So let's try to kind of associate this with what the problem is saying. Now this one says we had heads 4 times, and now the 5th one is also going to be heads, but I'm going to talk about it a little bit different here. In geometric, this is talking about the what? So this is talking about probability of failure and number of failures. This would be talking about success. So in the context, this would make most sense as the first heads was on the 5th flip, which could work the same way if I did it with tails, but that's not exactly the wording of the problem, but it kind of makes sense with where things go here. What does the probability of 0 mean? Just in general. Can't happen, impossible. What does probability of 1 mean? Definitely gonna happen. This problem is wordy, but what is the actual question it asks you? So the next time I flip this coin, what's the probability that it's heads? Do I need to give you information about what's happened the last couple times I flipped it? No. So all of this is irrelevant. And it's irrelevant because coin flips are independent. All I need to know is when I flip this the next time, what's my probability of getting heads? I don't care what happened before that. It's still going to be 1/2. What questions do you have off of that? Because I've talked about a bunch of different problems that weren't really within that problem. Yeah.
So what happens if I go on? We never place all of it.
No. So okay. So if I were to type this in my calculator, and I wanted to solve for this exact answer the exact way it is, what would I do in my calculator? And then we would have an n of 5, x of 1, p of 1/2. And why do I know it's CDF or PDF and not CDF? Because it's of getting exactly 1 correct. So you need to know how to see this equation in an answer, but you never have to type it in this way.
If we said, what is the probability of heads on 5 flips in a row, then which one would that be?
None of those. What would the answer be? Okay. Yes. So if I were coming to this problem and sometimes I need to think about it, I would think, what would each of these be? And then so it ends up being, how many do I want?
So what do you use
If it said, so if this one would say, I want exactly 1, but I don't care which one it is. I'm surprised we haven't come across more of those. I will definitely take time to go over probability questions. I wish I wouldn't have assigned the probability homework when I'm still going over this. So I know at least both of the last 2 nights, were they probability or was it 2 nights ago? We're in the probability part with your homework. Keep questions, write them down. I definitely want to address. Did I talk to y'all about where stuff was in the book for this class? Inside flap of your book, it gives you this thing you probably don't care about. It tells you basically topics that are discussed, but it breaks it down into 4 pieces. So it says exploring data, describing patterns, and departures from patterns. That's socks, making graphs and stuff. That's 20 to 30% of your exam, and it tells you that. Sampling and experiment, planning and conducting a study, which is chapter 4, that's 10 to 15% of your exam. Probability, that is 20 to 30% of your exam. And then statistical inference, estimating, population parameter, hypothesis testing, that's 30 to 40. That seems like a lot, but you realize since we started chapter 8 to chapter 12 was all of that, where it kept doing the same thing over and over and over. That's why it looks like it's so much. Just to give you an idea of breakdown, that's a good thing to go over, and I'm going to start giving y'all out stuff that y'all can do at home. This is a good checklist mentally to kind of go through this and be like, do I know what it is? Do I know what it is? Do I not? Maybe I should look it up. Not to necessarily write stuff down, but if you look through one of these topics and it's saying, hey, this is our structure for the whole class, and you don't know what it is, it's probably a good place to start. Also, in the back, that's your 4-step process as far as your conditions and your equation. For all of them, it says conditions for every type of problem and equation. It's another good place to look. But I'll go over a lot of that stuff after we get through this. All right, so 25. And the table above shows heights in inches and the arm span in inches for 10 randomly selected high school students. Which of the following significance tests should be used to determine whether a linear relationship exists between height and arm span, provided the assumptions of the test are met? What is the most important part of that whole question? What's the only thing that can measure a linear relationship? That is the only one that tests for a linear relationship. A and B, 2 sample, well, is that a 1 sample or 2 sample? 1, we took 1 sample and asked that one person 2 things. So it's definitely not this, it's definitely not this. What kind of test do you do for goodness of fit? Give me an example that I've used for goodness of fit. So it's like 1 column and they're just different categories. So like the colors and the M&Ms thing. Well, that's definitely not going to fit. At the very least, you've narrowed it down to 2. And then chi-square independence. I don't want to talk about that now. I want to talk about it with homogeneity. I want to do that one. Automobile brake pads are either metallic or non-metallic. An experiment is to be conducted to determine whether the stopping distance is the same for both types of brake pads. So just in those first 2 sentences, what is my explanatory variable? What is my response variable? In previous studies, it was determined that car size is associated with stopping distance, but car type is not associated with stopping distance. And we want to know about blocking. All right, so let's look at just what we wrote over there. Do we want to block on our explanatory variables? No, we're testing our explanatory variable. Do we want to block by our response variable? No, I don't want to group you by how you're going to respond. So here, car size is associated. Car type is not. So which one is going to affect our response variable? So this could possibly be a source of what? That's an external variable that would affect our response variable. So do we want to block on that one or the one that doesn't affect it? If I think car size is going to be different with my stopping distance, I want to split them first so that I can see is the difference based off of car size or is the difference based off of what I'm actually testing.
So with like any of the experiments, you always have to block by what the
Yes. If I am dealing with something like a protein, and I take a group of people, what kind of people do you think are going to be affected differently by something like protein? Like one group of people are going to be, it might work really well for than another group. What's an obvious example? Age difference. So I want to put old people over here and young people over here, and then basically look at it like a separate test. So I'm not accidentally getting differences because of age. I'm only getting differences because of the one thing I'm testing. You block by a variable that might directly affect your response variable. Number 8. A high school physics teacher was conducting an experiment with class on the length of time it will take a marble to roll a marble down a sloped chute. They ran repeated trials in order to determine the relationship between length and the time. So we're probably doing something like we were just talking about. Oh, here it is. Linear relationship was observed, and the correlation of coefficient was 0.964. What 2 things I can determine out of correlation there, aside from the question. Correlation coefficient is 0.964. Tell me 2 things about the relationship. It is positive and it is strong. After discussing the results, the teacher instructed the students to convert all of their length measurements to meters, but leave the time in seconds. So my x variable was what? Centimeters? My y variable was time in seconds. They want to switch my x variable to be length in meters. But keep my time in seconds. I'm not drawing something pretty. Let's just go with, here's my length, here's my time. Let's say my length right now is in centimeters, which would make it like, I don't remember the conversion. What is it, 33? What is it, centimeters to meter? 30 or something, 33. Let me do something easy. Let's do feet. As right now it's in inches. I switch this graph to feet. Tell me what changes about my graph. Does anything about that relationship between the 2 change? So if you change the units of one of them, what's going to happen to your correlation? If you switch your x and y, it's the same because all I care about is that line. All I care about is that line. If I switch these, I'm still concerned with this part of that line. If I multiply, I'm still concerned with that part of the line. Basically, R doesn't read. It doesn't read numbers. It doesn't read words. All it cares about is how much I can compress them together. So changing any of that stuff does not change R.
So even switching steps around doesn't do that?
Because all you're looking at is like how much I can push them together this way. So even if it was like altered like this, I'm still pushing them the same amount. Number 33. Trying to see if this is what I wanted to do. Okay, so an independent firm, they did a study of 100 children with math tests, with math scores. The results showed no statistically significant improvement using alpha equals 0.05. The program sponsors complained that the study had insufficient statistical power. Assuming that the program is effective, which of the following would be an appropriate method for increasing power in this context? Not thinking through the problem first, is it easier to overturn with, okay, improved math skills, is this one-sided or one-tailed or two-tailed? One-tailed. So using a one-sided instead of a two-tailed, that's not right because we used a one-sided at first, right? All right, would me switching to being two-tailed make it easier to overturn? It actually makes it harder to overturn. And I'm talking through this a long way than the short way here. If I switch this to a lower alpha, would it be easier to overturn it? I would need to make a bigger alpha because our p-value needs to be less. If I need it to be less than a smaller number, now I've made it harder. So it comes down to D or E, very generic. If you want to make something better, what should you do to your sample size? But just going over this thing in about a minute or two. Which error is this one? What's our probability of type 1? Because 1 is alpha, 2 is beta. Type 2, probability of type 2 is beta. Which path is power, the second one or the third one? Did these two work directly or indirectly? If I'm either going this way or this way, they work indirectly. If I want one to go up, the other one's going to go down. What about these two? If I want my type 1 power to be less, I have to make that one be higher. So how would I, if I wanted to increase power, I would do what with alpha? Increase it. I would do what with beta? Decrease it. My only option up here was alpha, which I would need to increase, which didn't work. How do you always increase? This is what I call ideal scenario. How do you always make something better? Increase your sample size. You have more power.
So those both are indirect?
Yes, both of those are indirect, which makes alpha and power direct, but then it looks like a lot of writing. Let's probably stop there. Oh, this one, I can talk through this one in a second. This one says it's a 70% chance, y'all can put stuff up. It's a 70% chance that her flight's gonna be on time. The best option is, how did you come up with that? Well, if I did that scenario over and over, about 70% of the time, it was on time. And a lot of people picked, of all flights arriving from California, 70% are on time. That's not specific enough. It's all of them like that one that she was on. 70% of them were actually on time. I'm going to make videos for everything that's left, though.